The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Great. Okay. Hello, everyone. Good day, and thanks for joining us in today's session. Today, we'll be covering the design principles for building high-performance clusters. And just to give an update, unfortunately, last time we were not able to have this presentation. So we are combining the Wednesdays and today's session into one big 2-hour session. And we'll be doing it in two parts. We'll take the fundamentals first and have a 10-minute break, and then we'll continue with the advanced portion. During the break, you can shoot out all your questions, and you can keep sending out questions before that as well, and we'll try to answer as many. And then we'll take the advanced portion and finish off. So with that, let's start today's session. My name is Ashrut Tambasta. I'm a principal architect at NVIDIA, and my domain of expertise is in networking, and we'll get into the fundamentals of networking as well as how we build large clusters in today's HPC data centers. So when you look at networks, what does first come to our mind? You know, why do you need or in a large high performance computing cluster? What is a cluster and why is there a cluster? So let's go back a little bit and see why networking came into being. Okay? So main thing was that when a processor was created, right? Now you wanted more and more power. People wanted more and more compute, and therefore the only way of increasing more and more compute was to make the processor faster, or was to actually have more and more such processors. Okay? when you have more and more processors, you actually need to interlink all of these. You need to interlink multiple compute elements, and then you can share your load across multiple compute elements. So many things came into being. You must have heard the term SMP, symmetric multiprocessing systems. Then clusters came into being. You look at things like cache coherency. You look at concepts of message passing between various compute elements. And when all these elements come into picture, you look at bandwidth and latencies. So today we're going to cover all these fundamental concepts and kind of build up on what you already know as standard networks to how you end up making a high performance cluster using a high performance network, or what is the difference between the standard networks that you see in an office environment or in your home with traditional gigabit LAN and Ethernet, or the Wi-Fi routers, or even a large telco network versus what you do in a large HPC and AI kind of cluster. So let's go forward. So traditionally, I mean, this is a very popular picture, right? Everybody kind of recognizes this. This was one of the first Cray machines, which actually enabled connecting four CPUs together, and all the four CPUs shared a certain central memory, and they were also connected to each other for running a parallel workload. Okay, and to connect all these elements together, there was some inter CPU communication and control. This is where networks for HPC comes into picture, right? You need to have some sort of mechanism to distribute the workload between various CPUs. You need to have this mechanism to coordinate between the various compute elements. You need to have this mechanism to do some sort of memory locking, so that if one element is writing on a certain section of the memory, then the second compute should not be overwriting that, and so on and so forth, right? So now this is traditionally how it started, but humankind has always been not satiated with simple stuff, so we wanted more and more. So he said, okay, now why don't we keep on adding more and more CPUs? And now you can see that over a period of time, or if you keep adding more and more CPUs, you cannot, the complexity that is required to connect them together starts increasing manifolds. The central block that you see on this picture, the inter CPU control and communication part, it becomes more and more complex, and there is only a certain limit to which it can handle the number of compute elements. And this is where industry started moving into something called clusters. And starting from that, standard typical SMP machines to these large modern supercomputing clusters is a journey of various technologies. We are going to be covering the networking portion of this. So in a modern supercomputing cluster, you do have hundreds and thousands and even tens of thousands of these compute elements. But now they cannot all connect into a central location, because imagine, what is the central location? It is, after all, some sort of logic. It's a silicon device, right, which will coordinate between all this. Now imagine if you have to connect 1,000 processors to a single silicon, trying to coordinate and do data passing between the compute elements. It's impossible to construct. And that is where standard high performance networks comes into picture, where now we are able to link tons and tons of CPUs together to create a single large supercomputer. The programming paradigms, the use cases have changed quite a lot, because if you look at a standard symmetric multiprocessor machine where a whole set of RAM was completely shared and exposed to all the compute elements, you cannot have it in a clustered environment. So a new paradigm of exchanging data came into play, which is called message passing, with which most of the people who are into HPC domain or AI domain are aware of, right? You need to have some sort of a communication library that packetizes the data from one CPU element and then sends it across to another element, and it does it using some sort of messages, which is what we call as an MPI, message passing interface, right? So uh, to do all that, you need to have the basis of connecting all these elements. When you say message passing, it's a very higher layer of abstraction. It is in the domain of coders. But before that, we need to create a cluster, and that is what we will talk about from the fundamentals. What are the design principles? What are the limitations, and what limits us in going from A to B? Okay, if let's say today I'm saying that we are able to construct a cluster of 20,000 elements, why can't I construct more than that? If I'm saying that today I have a certain amount of bandwidth between the elements, why can't I increase? Or why can't, what is the limiting factor? What technology defines the limits? So we will look at those limits, and hopefully people who are interested in this domain will be very interested to continue research and see it as a challenge. Okay, why is this limit there? What is the state of the art today, and how it can be improved? Okay, so with that introduction, let's get on to today's session. um, so when you look at the networking components for a high performance cluster, you actually break it down into three, four elements. Okay. You have, why do you need this networking? You need this networking because you have a large enough job which cannot fit into a single compute element. You need to distribute it amongst multiple compute elements. And therefore, you have multiple compute elements that you see on the left. You have some sort of interconnect media that you will use to connect this to another element. But now, since your cluster is not only a point-to-point connection between two elements, you need to have hundreds or maybe thousands of compute element. You need to have that central, interconnect unit, which is where we bring in a switch, a network switch, or a combination of multiple network switches, and therefore you have a end interface device which is called a network interface card or a host channel adapter in various terminologies. It is nothing but an interface which kind of talks to the processing element, is able to address the memory of the processing element, and it's able to send data from its port externally to a particular switch, which will receive the data, try to make sense out of it, and then send it across to its destination. Okay, so there is a element inside your compute which is the channel adapter or a network adapter. There is an interconnect media which are nothing but your cables. There are switches, and and the same thing repeated again, right, for the destination side. So we will look at all of these elements, and we'll mostly look at the fundamentals of the fabric, which is from the compute to another compute. What are the elements involved? So before I go there, let's do a little bit of history. If you look at the HPC interconnect history and development, it starts right down from, I think, the early 90s, where we had Cray as one of the leading supercomputing companies. They started off with a crossbar interconnect to link multiple of the compute elements. Okay, then there was an explosion of multiple standards and technologies by the end of 1990s. Okay, so towards 1999 and 2000, there were companies like Quadrix, Myricom, and Mellanox which standardized high performance interconnect for HPC and HPC cluster. Actually, there was no AI back then. Now AI comes into picture, and we will talk about how the fundamental requirements of AI are completely equivalent to what HPC systems need. Okay? So the systems that we design for HPC now are actually being called HPC/AI systems. So yes, many companies started off, and there were a lot of standards. Okay? The whole aim of all these standards was to have the fattest possible pipe between the compute elements so that we can transfer the highest amount of data passed in the least amount of time, which corresponds to your bandwidth. It also aimed at reducing the latency of these transfers, because every time when you were doing parallel compute loads, people would not do very large data set transfers. There might be simple communication wanting to, like a mutex kind of communication, right? Or simple flags, or simple single element data exchange. So it was imperative to have these network be very low latency, because whatever time that is spent by the data in flight is the time no compute can happen, right? If you're looking at synchronous compute and communication, the time spent on moving data from one point to the other is time wasted. So you had to have very small as the latency as possible. So the two fundamentals for high performance networks for building clusters was high bandwidth and low latency. And over the years, many companies, did a lot of things. And right now, if you look at today's scenario, two of the companies are surviving. One is Mellanox, which was actually purchased by NVIDIA, and it is now, which was the proponent of InfiniBand as an interconnect technology. The other is Cray, which got actually acquired by Hewlett Packard, HPE, and they propagate their own proprietary interconnect for making supercomputers. Some other companies came into being, but then they have stopped manufacturing HPC networks. Again, this is more of history and technology and companies where things stand today. But what we will discuss is the fundamentals, okay? And then we'll map it into the current generation. So let's go into the fundamentals. I thought of having this session with top-down approach, where we will talk about today's cluster, and then we'll drill down into the underlying technologies. But since this is more of a knowledge sharing session, so I thought let me do a bottoms up approach. So we start with the fundamentals. The fundamental is the physical layer. Okay, if you have to connect two elements together, you need to have some method of connecting it. And what are we aware of? Okay, so first of all, when you look at the physical layer, it is nothing but a wire. It can be a wire, right? You take two elements and you connect a communication cable between them. And what does this cable do? Well, actually, it just transmits zeros and ones, right? It sends out sequences of zeros and one. And there are various, people who are from communication engineering background. They know that there are various methods of sending these zeros and one. You can have different kind of coding. You can have higher frequency and so on. And that's what we do today. Okay. And the thing that we are most commonly aware of is a standard LAN cable, right? A LAN cable, RJ45 cable, contains copper conductors inside, and there is a certain speed at which you send the bits, you send the zeros and ones. In today's world, we are looking at sending the zeros and one over a single pair of copper conductor as fast as at 25 gigabits per second, or even 50 gigabits per second. Okay? And depending on what kind of signaling are you doing, if you're doing non-return to zero, where a zero corresponds to 0 volts and one corresponds to a high voltage, or you can divide the levels of analog signal by in multiple levels, represent every level to a particular bit pattern. So you do amplitude modulation, right? So you do different kind of signaling, but it is the media that transmits the data between these two compute elements. Now, one nice thing we've seen, over the years, there are so many ways of doing this thing. Okay, and every time what happens is, one company propagates a particular standard, another company propagates another standard. Okay, one says, okay, my analog designers are good to send bits very fast, so they can design their ICs so that the switches are very fast. Okay, so I can do 25 gigabits per second, but another company says, hey, I've got engineers which cannot design the on-off control so fast enough, but they can do it very accurately. So I can do multiple levels of analog voltages. Okay, so I will propagate a standard which is non-return to zero, and it does a modulation, different kind of modulation. So there are so many things. One company says, okay, I will send it across one pair of copper conductor. Other company says I will send it across four pairs because I can do parallel. Okay? So all this resulted in multiple competing standards, and then there's always a consortium of companies. They come together and say, hey, it's ridiculous. We need to develop one universal standard that will cover everything and it will cover everybody's use case. And eventually, what happens? It results in another standard, a 15th standard, right? So now there are 15 competing standards. Again, there is no, I would say, there's no way of addressing this. This is how it has been, and therefore we try to achieve as much standardization as possible. But because HPC and AI, or high performance networking for HPC and AI cluster, is such a niche, I would say, field, that whoever does things the best and the fastest gets a standard, okay, or puts things in a standard. So let us look at, when we talk about standards, let us look at some simple things. I'm talking about connecting servers together, right? When I'm talking about connecting servers together, I'm looking at these physical media connectors. Okay? You all are aware of these standard LAN cables. It contains multiple copper conductors inside, and it connects to your simple RJ45 port, and it basically sends out data. But this, as you all know, is not very suitable for very high speed networking. What's the maximum that you see? You see a maximum of 1 gigabit per second, or you see a maximum of nowadays 10 gigabit per second, right? In HPC or AI clusters, we are looking at 400 gigabits per second. Obviously, these standard links are not capable of carrying that much, and we will touch a bit of why they are not capable of carrying that much. Okay? Therefore, you have standards which are based on SFPs, standards which are based on QSFPs. These are various connectors which are used to link two systems together, or link a system to your switches. Okay? And they have different capabilities. But the fundamental capability comes from the fact that you need to send data as fast as possible. What are the knobs that you can tweak to send this data fast enough? What you can do, we talked about simply encoding, right? So you can encode more rather than having a voltage level represent a 0 and a 1. You can actually do encoding so that you can carry 2 bits in every clock cycle. You can increase the clock cycle itself. Rather than clocking data at 25 gigabits per second, you can do it at 50 gigabits or 100 gigabits. You can use multiple physical channels, so that when you connect two systems together, if you go in your normal RJ45, there are four twisted pairs, right? Why is it called UTP, twisted pair? So unshielded twisted pair. There are four pairs of copper, so you can have more parallel lanes to increase the bandwidth. Okay? Or when you're going optics, you can start multiplexing multiple wavelengths into an optical fiber. So all of these parameters have got certain limit, and limits are very much related to current technology, physics. So I will just concentrate 5 minutes on one of the limits, or how this limit is reached, right? Let's look at a standard high-speed channel between a transmitting element and a receiving element. That means between server 1 and server 2. Whatever is there inside the server, it's a black box. So this triangle, it is the transmitter. It represents that black box. It goes into a connector. The connector goes into a channel. The channel can be a cable. It can be a backplane of a large supercomputer where you plug in multiple servers as blades. Okay? That channel carries signals. There is a receiver connector, and then there is a receiver amplifier, and therefore this entire thing forms a high-speed channel. What now, when we are sending data on this high speed channel, You send it in zeros and ones. You must have seen in many, interconnect related blog posts or papers that you study, you always see something called an eye diagram. Whenever there is a high speed network shown, it shows a very nice, diagram which looks like an eye. This one is not looking like an eye, but I just want to show you why I have it here. What is an eye? What is this diagram? It's nothing but a representation of the bits that are being sent from one server to the other. The bits are these zeros and one. Every 0 and 1 has got a bit period. The period of this bit is nothing but the reciprocal of the frequency. So if you're doing transmitting data at 25 gigahertz, the bit period is certain amount of nanoseconds. So if you plot all the bits in that window and then overlap all the other bits, you will see something that looks like an eye. Okay, where x-axis represents the period of your bit, y-axis represents the amplitude of your bit. If now let me go here, this looks more like it, right? This looks like an eye. This is nothing but the bits that are actually traveling through your interconnect channel, and this is what people who are electrical engineers who are working on circuits with high speed networking would see. This diagram just represents that if there is a zero, or if there is a which is mapped to the negative voltage, if there is a one, it is mapped to the positive voltage, and the margin in between where I have no bit present or no sample present is my margin. That means my receiver can distinguish between a 0 and a 1. Why it can distinguish between a 0 and 1? Because the voltage levels are distinct over here. So if I have a comparator, I can make out what is a 0 and what is a 1 by comparing against a level crossing. Okay. When we are transmitting this data through a channel, the bit period or the eye diagram starts looking somewhat like this. The eye, this is what we say, that the eye is closing. What it means is, now at the receiver end, I'm not able to make out, or there are times when the channel is very long, the eye completely closes. So there is no more black portion in the center over here. Therefore, my receiver cannot make out whether it has received a 0 or a 1. So this defines one of the fundamental limits. Okay, why? Unless and until if you are able to make out between a 0 and 1, you have not actually transmitted data from the source to destination. What defines this fundamental limit? This is where we come into. So I'm getting into why, what are the limits right now, or why we cannot, why do we have only 10 Gbps? Why cannot I make 1 Tbps today? Okay? The reason is that I have a certain media, okay, and it has got certain characteristics. It has got certain kind of loss characteristics. Every media has got frequency dependent, I would say, conductance, right? So when you start increasing the frequency of the electromagnetic wave that you're transferring, the amount of resistance that it offers, it increases. There are more losses, okay? And channels are not capable of keeping up to a certain speed limit. Why they are not able to keep up with a certain speed limit? Again, you go into the physics of it. There are copper losses, there are reflections. I will talk a little bit about that. But what happens is, why do you see that closing eye? You see that closing eye because when you are transmitting zeros and one, it can be any random pattern. It is not 0 1 0 1 0 1. It can be multiple zeros followed by multiple ones, or some zeros, some ones, or it can be even 0 1 0 1, depending on what signal is going. When you look at that bit period or that bit diagram, multiple zeros followed by multiple ones, it's a lower frequency, right? Because the time period is high. When the bit pattern is a continuous sequence of zeros and ones, the frequency is higher. So you're actually transmitting a wide range of frequencies. It's a wide band. And obviously, when you transmit the lower frequencies, the attenuation of the media to these frequencies correspond to this side of the spectrum, the left side of the spectrum. When you go on higher frequencies, you have more attenuation. That is standard property of copper conductors. When you're transmitting electromagnetic waves, it's a transmission line. There is obviously a dielectric. There is a ground reference, there is a plus and a minus, and there is a dielectric in between. When the electromagnetic wave is going through the media, the dielectric also needs to polarize and depolarize at the same frequency at which you are transmitting the waves. Obviously, this dielectric's ability to polarize and depolarize causes frequency dependence of insertion loss, and because of which higher frequencies get attenuated more, lower frequencies get attenuated less, and you see a closing eye. So these are some of the limits, and therefore, industry obviously moved to optics. There are tons of optics out there now. Why? Because, well, insertion loss in optics we know is very less. Okay, when you're sending an optical wave, it goes through optical fibers and you don't get so much insertion loss. So now I can carry longer distances, I can carry more speeds. But when you go into optics, you require more power, require more energy, you require more complicated electro-optical converters. How do you launch data into the optical fiber? Basically, it's nothing but a laser which is being turned on and off at the same frequency as your data rate, right? And the laser, when it turns on, it sends a pulse of light, and the photo detector detects it and then converts it back into electrical signal, makes it a 1. If the laser is off, it is a 0. There are other technologies that people work on now, which is related to photonics, where you also try to modulate, instead of turning the laser on and off, you try to modulate the laser so that you operate in a region where you have lesser delays between turning on and turning off, and therefore you can transmit data faster, and so on and so forth. So starting from standard LAN cables, or if people, people from the 90s would also remember standard modems, right? Cable modems, telephone modems, in which we used to get kbps of speeds, right? Because it was, a certain kind of media. Uh, Standard UTP connectors would give you that time 100 Mbps. So starting from that, today the industry is able to do with single ports link speeds of around 400 gigabits per second. So this is where we solve the bandwidth problem. And of course, there are developments going on in which we would actually increase it from 400 to maybe a terabit per second and beyond. So this is on the physical side. Definitely, we don't want to spend all our time on the physical side. So let me come into the next side. Let's say we have created good enough physical media and we are able to send data from one point to the other. But when you are trying to create a cluster, it is not point to point, as I mentioned previously, right? So you need to connect it to some element. So on top of the physical layer, now comes the network layer and routing. Okay? So before we get into the network layer, we need to look at a switching element. I'm giving an example of an InfiniBand switch because I come from NVIDIA. We use InfiniBand. We also use many other kind of interconnects like NVLink. Industry uses many different kind of interconnects as well, but this is one of the most popular interconnect for HPC systems. InfiniBand constitutes around 90% of top ranking systems, right? What is this switch? Well, it's actually a silicon device which has multiple ports, as you can see on the front panel. On these ports, you connect the physical media that I talked about. You connect a copper cable or an optical transceiver. Okay? The transceiver or the copper cable is receiving data from one server. The data comes in at a very high rate. We are looking at this one is, let's say, 200 gigabits per second. The data comes in, and now the silicon needs to decide what to do with the data. So obviously it contains some sort of header. Header contains the source destination, the source address, and the destination address. So the silicon inside this switch is required to look at the destination, and then it is required to check from which port it should send that data out so that it will reach its destination. For doing all these checks, it needs to have some sort of a table inside. Okay, so that and the table needs to know, to reach a certain endpoint, what port I should use. This is where the concept of switching and routing comes into picture. And the time taken for this silicon, or the time taken for this ASIC inside the switch to take a packet in, decide where to send it out, and to send it out, is the latency between its two ports. And this is again one of the most important parameters for high performance network. When we talk about latencies in today's terms, it is of the order of 130 nanoseconds for this particular switch. That means one data byte coming in, or a packet coming in from port number one, after 130 nanoseconds will appear outside a destination port. Okay, so but to do that, first we need to create a network, right? So how do we, what do we do? So if you need to create a cluster, okay, a small cluster, you will take multiple servers and you will, let's say, connect it all to that particular switch. The switch, as you saw on the previous diagram, contained around 40 ports. So data, it can actually connect 40 different compute elements together, and it can form a single cluster. When you want to make a larger cluster, you need to, how do you do it? Either you can increase the size of the switch, or you can try to connect multiple switches together to create a particular topology. Now, obviously, the limitation of what size a switch you can make, you would see there are large switches as well. If people are from the Ethernet world, you will see there are switches which contain 1000 port or 500 ports or 40 ports or 100 ports. Even in InfiniBand, there are switches which contain 1600 ports. But this is not a single switch. It is actually a big device which contains multiple ASICs inside, and they are connected to each other in a certain way. A single ASIC, there is limit to how big an ASIC you can make. One of the simplest limit is the die size. You take a large wafer, and to get good amount of yield, you will have certain size of die on it. A certain size of die will be able to service only certain amount of ports, because finally you need to take electrical signals out of that die. How many ports you can take out of that die would depend on how many pins or ball grid arrays you will have from that silicon. It's a very simple way of saying that, okay, I cannot take a 2-inch by 2-inch die, because then my yield is not very high. So we always, industry always tries to do the best price performance, and based on that, the largest radix, or I would say the largest port count processor, network processor that you see today, is of the order of maybe 40 ports or 128 ports, ranging between that, right? And obviously, you know that there are clusters which contain thousands of compute elements. So if a single chip has got only 40 ports, how will you make thousands of compute elements? So how will you connect thousands of compute elements? So you start making these topologies. Okay, now topologies in a high performance computing cluster cannot be random. Why? So the whole World Wide Web, the whole internet is a particular topology, right? Every endpoint is connected to every endpoint through some link. But the way I'm presenting over here right now, my computer is connected to my service provider, to my society's fiber box, from there to my service provider's distributed unit, from there to a core switch, from there to one of the major routers or the gateways in India, in Mumbai maybe, from where there are some inter-sea cables, it goes somewhere. So Ethernet, World Wide Web, it's a connection of all these elements, and you have a standard protocol running through all this. In an HPC cluster, you cannot do just random connections. Why? Because the aim is different. The aim is that all compute elements, it's a democracy, all compute elements have same kind of capability. Therefore, they should have same kind of network bandwidth and latencies and delays. Therefore, you need to connect them in a well-defined manner. And because one of the another reason that you need to connect them in a well-defined manner is because, and we'll come to that, is because you need to get them to talk to each other in a in a symmetric way, right? And therefore we create, I will not go into the loops, let me go forward. So you create a certain network topology which is defined by equations. Therefore you can have equation defined routing to be done between these elements. There are various kind of network topologies. We look at standard tree topologies, fat trees, hypercubes, toruses, dragonfly. What is common between all these, and what is the difference between this and a World Wide Web mesh, random mesh? The difference is that all of these topologies are very nicely mathematically defined. Therefore, you can define routing between all the elements which constitute this particular network. And this is where the network layer, the link layer and the network layer comes into picture. Uh, these are some examples of topologies. If you want to make large clusters, you'll end up putting multiple of these switches. You'll connect uh, them to each other in a particular fashion. You'll create multiple layers, and therefore you can create very large clusters. I'm talking about a normal 3-level class topology, because let's say if you connected only two, you took only two switch, the maximum compute that you could connect is equal to the number of ports of these two switches minus the number of ports which are required to connect the two switches together. So if it was a 40 port switch, maybe you could connect 30 servers to switch 1, 30 servers to switch 2, and there were 10 links between the two switches. If you want to grow more, you could create a triangular or ring network. If you want to grow more, you start making these kind of trees, okay? Or you start making these kind of toruses. Here every box represents a switching element. Every arrow represents the link between the switching element, okay? And then you keep on folding these connections and you create a very nice, well-defined, mathematically explained topology. Therefore, you can actually put this equation into the routing engine of the switching element, which will now know where to send the incoming packet if it has a certain destination address. High performance network need this deterministic routing, and there are now adaptive routing as well, which we'll cover in the next session, next part of this presentation. But the bottom line and the takeaway is, to create a high performance cluster, you need the network to be well defined so that the routing elements are they contain routing tables which are given by an equation, so that they can send out packets without any issues or without any delays. Okay? More than that, you always want, whenever we are creating clusters, we always want there should not be any packet drop. In Ethernet, we are allowed packet drops, right? Why? Because, well, it connects to the entire World Wide Web, and there can be congestion. If it is not 100% reliable thing. If there are problems in the middle, you can drop packets, and then the software can request for retransmission. In HPC, if you have the software trying to request for retransmission, the whole process will become so slow that you cannot actually scale your application. So you need to have a routing which is credits based, as in every element knows that it has got a path available to its endpoint, and therefore every source can send data to the destination without dropping packets. If you just now look at, now let's go one step back. So let's complete the link layer and the network layer portion. So as I said, we are sending zeros and ones. Zeros and ones are bytes which are put into packetized formats from the server. The packet contains maybe some a delimiter to basically tell the server that, okay, one packet is coming, send it out. It will contain a local routing header, a global routing header, some transport header. It's a standard OSI 7-layer model, which is actually the basis for most of the network. Actually, I would say all of the network. Okay, so there will be some identifier which says where is my from where I'm coming. The main payload is this in the center. but there are bytes which define, hey, from where this payload is coming, for where this payload is intended to go. At least this much is needed, right? And then what kind of operation is it? So all this comes inside the packet format, comes into the network layer and the transport layer. Okay, so we covered till physical layer, link layer, and networking layer. Let's go into the transport side. Right? Transport layer is the entity which defines for high performance computing cluster. It defines so for normal, normal Ethernet, you know there is sockets, like there's a sockets interface. If you try to send data between two servers, you send it through sockets. In high performance clusters, you don't open sockets. If you open sockets and you put data into that, it needs to be processed by the kernel and the driver. Okay? So actually, if you look at it, on the bottom side, on the top side is what happens in a typical TCP/IP protocol. The application, which is a routine, let's say it's a routine which contains data in a particular buffer, and that buffer is part of the, obviously, the RAM. Okay, the application copies that buffer to the sockets layer, that copies the data from its own buffer to the transport and protocol driver inside the adapter in a server. The adapter breaks it down into, in Ethernet we call it MTU, right? So it has to break it down into a particular transfer unit, and then it will send it out through the physical adapter, through the cable that we talked about, or through the interconnect media. There can be switches in between and connected to various topologies. The job of the switch is to look at the source and destination and route it accordingly. We are assuming that it has routed it correctly and it has reached the destination. That in the destination, again, there will be multiple copies of that data between various portions in the buffer, and the data will reach the target. This whole cycle of copying data from server to a client, or server number one to server number two, is the latency. Let's say I wanted to send only one floating point in number, a double precision floating point number, from server number one to server number two. In today's world, we take around a microsecond. Okay. In TCP/IP based connection, we take around 10 microsecond. Why do we take 10 microsecond? Because of these so many buffer copies are involved. Therefore, for high performance network, you need to have the transport layer which kind of bypasses all these intermediaries. It bypasses the entire kernel driver and protocol driver and buffer copies and so on and so forth. And which is where an example like InfiniBand, which does something called remote direct memory access, RDMA operation, where it can actually read data from buffer of one application, which is in the RAM of one application, and put it across to the memory or in the RAM of the second application. Because it is able to do that, the latencies are of the order of some microseconds, or actually some hundreds of nanoseconds in today's world. If you take two servers, okay, let me come into real world, right? Today's world right now. If you take two servers, GPU enabled or not, connected with a wire through an InfiniBand adapter or any high performance network adapter, and you try to do a ping pong between the two servers by exchanging maybe few bytes, okay, you will be able to do it in around 600 to 700 nanoseconds, because we bypass all these points. Okay? Now comes another important concept of having accelerated computing. We all have been doing these sessions for GPU accelerated computing. I'm sure you've gone through sessions where people talked about GPU acceleration, CUDA programming, and kind of offloading parallel workload onto the GPUs and so on. When you do that, and as long as things are confined within a single GPU, it's fine. But now when you want to create a cluster of GPUs, again, you need to transfer data from one GPU to the other. So currently, if you look at how systems are made, you would have a CPU. You just open if you look at a motherboard of a standard server, you will see a CPU. you will see a chipset, some PCI Express switch on it on the motherboard. The CPU will have the DRAMs, which are the memory. It will also contain a GPU. Okay? The GPU will have its own GPU memory, its own RAM. When you are trying to accelerate a workload onto a GPU, you will actually copy the operands from the CPU memory onto the GPU memory. And the GPU will then do some matrix vector multiplication, matrix multiplication. And then after certain iterations, if it needs some newer operands, it will write down the result onto the CPU memory, get some new operands. Okay? All this communication is done from the CPU and the RAM through the chipset to the GPU memory. What if we wanted to send data across two servers containing GPUs? Let's say my matrix was quite big and I want to send from memory of GPU number 1 to memory of GPU number 2, which is a different server. So now I need to copy my data because I'm able to do DMA operation from only the system RAM. Okay, because a normal adapter card, let's say if you take a standard Ethernet or any adapter card, it is an IO device. It sees
some queries like 810 दिलेलं की आमचं काम झाल्यानंतर सिस्टम फॉर्मॅट करायची परमिशन भेटते. तसं काही
Sorry, is there a question or no? Okay, so
कारण
Okay.
डेडिकेटेड तर नाही आहे ना डिश त्यांच्या साठी.
It's a system like they have to use it like any other user.
They can delete their area themselves.
And moreover, their home area, any other user will not have access to their home area.
Ashish, can you mute?
You can say direct to them. जी काही Linux security असते basically पूर्ण it is in place. Second,
Bharat,
they
I
are
think
data
Ashish
access
is not
only
able to
by
hear me.
them. So that was and this task is confidential and as per NDA, however.
Okay, now we are good. Thanks. So when you're looking, so we were in sending data from GPU or memory from system number 1 to memory of system number 2. Okay, when you want to do that, you can only address the memory which is in the system, which is the RAM. When you want to send data from GPU memory, you will need to copy the contents of the GPU memory into the system RAM, into the area which is addressable by the GPU, and then there needs to be a memory copy done between the area which is addressable by the GPU and the RAM area which is addressable by the network card. You need to do that copy, and then the network card can do a DMA operation, which I explained in the previous slide. What we did was, rather than doing this memory copy, okay, we worked with systems where we worked on chipsets and technologies where we said, okay, let's have a unified memory in the system RAM, which is addressable simultaneously by the GPU as well as the adapter. Obviously, there are lock mechanisms implemented in the control plane so that you don't end up corrupting the memory. But once GPU has written its data onto the system RAM, the adapter can access the same area in the system RAM and do a DMA operation to the other side. And therefore, it gives a good amount of acceleration because now you have completely avoided the memory copy within the system RAM. We went one step ahead and said, hey, if I have to exchange data from one GPU's memory to the other GPU memory, why should I even copy it into the CPU memory? Why can't I have my network card directly access the GPU memory and therefore save up all the cycles of sending data from GPU memory to CPU memory? And this was also done. So these technologies in the transport layer, these are all part of the transport layer. Okay, these technologies in the transport layer of network are called RDMA, GPU direct RDMA, GPU RDMA sync, and so on and so forth, fancy words. But all they do is, in that packet that I showed in the previous slide, apart from the source and destination identifier address, it contains a transport header, which is nothing but a DMA pointer to the memory location of the destination where the payload needs to be put. On reception of that packet, an intelligent adapter makes sense out of the transport header and puts the data directly into the GPU memory. And therefore now you can get huge amount of bandwidth gains without using any of the CPU cycles, and huge amount of latency gains as well. So whenever you hear the word GPU RDMA or RDMA, this is the technology that people are referring to. There are, I talked about like there needs to be a control plane which ensures that data corruption doesn't happen when 2 3 devices are simultaneously accessing, or when to packetize and what to send. So there is a control plane. Earlier the control plane was actually controlled by the CPU. So, and only the data plane was accelerated. Now with the latest technology that you will see in the GPU clusters that you are actually being exposed to, even the control plane is running inside the GPU in sync with the adapter. So there is no involvement at all of the CPU for GPU to GPU communication, and therefore we end up making a very efficient GPU accelerated cluster of multiple hundreds and thousands of nodes, which we will talk about in the coming slides. Okay, so just to conclude this part of the presentation, I think we are 5 minutes over. Just to conclude this part of the presentation, we talked about the fundamentals, we talked about latencies, we talked about bandwidth, we talked about what are the limits to this bandwidth. So let me just give a quick picture of latency. Why are we doing this RDMA, GPU RDMA? Because we want to have as low latency as possible between all communicating compute elements, whether be it accelerated computes with GPU or standard x86 CPU or ARM CPUs, right? We want to reduce the latency. Latency is a combination of all these factors. It is a combination of the cables which are there in the network. It is a combination of the switch and the topology. I'm showing here a big switch which contains multiple individual switches in a particular topology. It is a combination of how fast the network adapter on the endpoint is able to look at the packet and do a DMA operation. And eventually, what a programmer sees is the MPI latency, the message passing latency, or the communication framework latency. In when you take the example of the communication libraries for maybe a TensorFlow or a PyTorch, right? So just to summarize, the latency of the media is actually 4 to 5 nanosecond per meter, and it's a hard limit. Why? Speed of light. Okay? Light travels at a certain rate, 3 lakh kilometers a second, which corresponds to certain nanoseconds per meter. In a media, the speed of light or the speed of the electromagnetic wave is defined by the speed of light divided by the refractive index if it is a optical media, or divided by the permittivity if it is a standard dielectric media, which corresponds to usually 5 nanosecond per meter. It's physics, you can't change it. So if you have a very large cluster, okay, people sometimes ask me very naively that, okay, why can't I have a very large supercomputing cluster by combining all the computers in a city? You can do that. You can run problems which are embarrassingly parallel, which you can divide amongst all the compute elements, and they don't need to talk to each other so frequently. You can do that and you say, okay, I've got a big system. But when you're looking at scientific applications and we are looking at coupled applications, you need to talk very fast. Okay? And that's where if you make clusters which are very large, you actually keep on adding latencies. When you look at optical cables, you add some more latency for the electro-optical and opto-electrical conversion back. When you make a large cluster, you will have to have multiple of these switching elements, as we talked about. The switching elements have certain amount of latencies between them. I said 100 nanosecond, 130 nanoseconds, right? Then there is this transport layer, which presents a latency of around 600 odd nanoseconds. Again, I'm showing the numbers just to give you a practical whiff. I'm showing you the numbers which are there for a high performance interconnect like InfiniBand. The highlighted numbers are what you see in a standard network like Ethernet. Okay. Again, physics does not differentiate between high performance network or Ethernet or whatever. So the latency of the media is the same for both the protocols, but the other latencies starts differing. Why? Because if you take a switch, Ethernet has a protocol which is designed for the World Wide Web. So it contains a lot of complexities in its headers. It contains a lot of things like, you have IP addresses, you have, protocol port numbers, and you have so many quality of service things, VLANing, whatever, right? Because that's how Ethernet was designed. Therefore, when an Ethernet switch receives a packet, to take a decision, the time it takes to make a decision of where to send depends on the complexity of all the headers. In a high performance network, you're not connecting it to World Wide Web. It is for a very fast set of computers within a data center. And therefore, you can do away with the complexities of all the other headers. And therefore, the switch can take a decision very fast. And therefore, the switch has very low latency. Okay. TCP, since you're allowed to drop packets, you don't do a DMA operation. You have 7,000 nanoseconds of latency when you want to do a single byte transfer from one computer to the other. Whereas high performance networks, RDMA enabled networks, are 1/10 of that. So with this slide, I'm just showing the differences between, if somebody says, okay, what is the difference between a standard Ethernet with that RJ45 versus a supercomputer that is in CDAC? Let's say, some Param Siddhi or Param Yuva that is in CDAC. Well, it contains right up from the hardware to the networking equipment to the software. It contains elements which are highly tuned and designed for high performance clustering and communication. So with that, I will stop here, and then for 5 minutes, I think I took some extra time. So I'll stop for 5 minutes, and then we will start again. In the meantime, Bharat, are there any questions that I can verbally answer? Okay, I have a question. How is RDMA able to access the NIC in user space? Doesn't this require privileged kernel mode access? Well, RDMA is in user space, but InfiniBand verbs is actually, kind of a intermediate. It's like a sockets. Let me try to explain it from sockets point of view. So yes, in Ethernet, sockets are in the user space, right? And then it sends things into the kernel space where it can actually map into where data is being read and written from. In InfiniBand, the RDMA protocol driver is actually, it's running in the user space, but it can lock memory into the RAM and it can do a DMA operation. Okay. It is allowed the network, the NIC card driver, RDMA capable driver is able, it can actually allow the NIC card to address the entire system RAM. And obviously, the driver is written in such a manner that the NIC card cannot go rogue and try writing anywhere. It will only write into that area which the application tells it that, okay, my data, the data that I want to exchange is residing in that particular area. Then the NIC card is able to go across the entire RAM, but it is through the application. Okay, is another question. What is meant by connecting multiple switches to form a single cluster? I didn't mean topology. Topology is nothing but a combination of multiple switches. Sorry if I said that is my mistake. Multiple switches form a topology. It forms a single cluster. Okay? The topology is nothing but combination of these switches. If you see my screen out here, you have all these points are switching elements, and I connect it in a particular defined manner. Okay, it forms a topology. Okay, and it forms a single cluster, not a single topology. Okay, there's a question. There was a comment saying the session is hanging between few seconds for only me. I don't know. Can anyone tell me if it is okay? I assume it is okay. Okay, so let me do the second session also. I think I just overshot by a few minutes, so we won't take a 10-minute break. We just took 5 minutes. So let's get on to the next session, okay, or the next portion of my presentation. So now let's try to cover some advanced technologies. We simply talked about very basic stuff. We simply talked, just to give a feel of InfiniBand, Ethernet, protocols, various layers, and how data transfer happens. But obviously, this is something that industry has been addressing for quite some time. Okay, so. Okay, before I go there, there are one or two more questions I saw. Let me answer that. What is a factory topology? Okay, hold on to that. I think I will have some more examples in this. Okay, so let's continue with this. I'll have some more examples when I go into the advanced technology section. Okay, so let's look at some advanced technologies and let's try to put intelligence into the networks. Right now, all the network did was work as a conduit, a very high speed and low latency conduit between compute elements. But we want to look at it now from an element which can do some more intelligence. Okay, so what do I mean by intelligent networks? Let's look at a simple, typical high performance computing operation, okay, or an AI operation. Why are we making this cluster? Why are we connecting all these computes together? So that we can run a very large single job by dividing it into multiple compute elements. When you do that, let's say you are doing a simple matrix vector multiplication, right? Any application which is trying to solve a partial differential equation will break down into a matrix vector multiplication or a matrix sparse vector multiplication. If it is a very large problem, it will be a very large metric which will not fit into a single system. And obviously, you need to break it down and send it across to multiple systems. When you have sent it to multiple systems, they will all compute their portion. Okay? After they have computed their portion, they will try to exchange the data to each other, or they will try to send their results to somewhere, right? So there are I would say operations in which you would distribute data and then you would collect data, one to many and many to one. These kind of operations in networking domain are called collective operations, and it is required for even in iterative solvers, right? You do one iteration and then you will calculate a new weight, and you will do another iteration and then again calculate a new weight, and so on. Let's say everybody is, one big job was distributed amongst 100 servers and everybody got their job, and now they will do their job and they will send out their results to a master processee which will collate the result, get a new weight or get a new answer, and then send across more data to the other processing element. And this entire cycle will keep on repeating till your iterative process converges into a particular solution, or till the residual error is within the acceptable limits. So every scientific application and every AI and machine learning application also does this kind of communication. Now you can see, okay, one question was, what is a factory topology? A factory topology is nothing but, so as I said, if you wanted to connect 100 computers and I had a switch which had only 400 ports, and let's say I wanted to connect, I had a switch of 40 ports and I wanted to connect 400 servers. How would I do that? I will take lots of switches. To every switch, I will connect maybe 20 servers, and I will uplink the switch to another layer of switches, so that now I form a two-layer topology where I have 20 ports connecting to servers and 20 ports uplinking to 20 different switches. Like that, I have a second switch as well, which has got 20 ports downlinking to servers, 20 ports connecting to again different switches. This whole thing forms a factory network. The way I have connected over here in a two-level distributed architecture, it's a factory network. Okay. If I have to cover topologies, it's a full session on its own. So let's not go there. But I just showed a simple factory topology to make a 400 node cluster. Now the problem is when I'm running a job where I have a master process which needs to collect after every maybe 10 microseconds or 100 microseconds, it needs to collect data from everybody else. This data collection is the master process is running on one particular server connected to one switch. Okay? Because master, as the name implies, can only be one. And all the slave processes needs to send data back to the master. So master will collect data from slave number 1, it will connect from slave number 2, from 3, and so on and so forth. It can collect only one by one. Why? Because master has a single link to the switch. You cannot say that, hey, why don't we have a master with multiple links to all the switches? Well, we can't, because then we will end up taking up the ports of all the switches and you can't make a big enough network. And you cannot always assign only one master. Master can be anybody, right? Depending on what is being solved here. So the topology, whatever way it is, if there is a master process, it will always result in getting data one by one from everybody else. Okay? When it does that, it's a in-cast scenario. It will take the data, it will do some operation like MPIs, it will do some average or whatever, it will do some mathematical operation and then share its data back. This is what is called a reduction operation. MPI all reduce. People familiar with MPI programming would know that. Okay, when master process, because it has to do this particular thing, because it has to take data one by one, okay, it forms kind of a bottleneck. Because if a cluster, now imagine a cluster which is 1000 nodes running a single job, the master needs to take data 999 times. Like it will take data from 1, it will take data from 2, and so on. So it will take 999 individual send receive steps, okay, before it has collected data from everybody, and then it will be able to do the particular operation. And once the operation is done, it can maybe share the data in a single step, because there is something called multicasting or broadcasting, right? The data is a single number, the result is a single number, which can be sent as a broadcast packet to everyone. But collecting the data is an n-step process if you have a n-node cluster. What today's networks start doing is we've made it intelligent so that we actually use the networking elements to also take part into computation which are not standard mathematical computation, but computation which are network oriented computation. Like when you're trying to run that reduction operation, the switches or network switches themselves can actually collect data in a single step from all the connected slaves and do a reduction. Reduction can be as simple as doing a sum or a minima or a local minima maxima, or doing an XOR or AND operation, depending on whatever application demands. Okay, so now that you look at it, every switch in the network can take data in a single step, because all the servers which are connected to it are connected in a parallel manner, right? So in a single step, it will be able to receive data from 20 servers or n number of servers, where now n is equal to the number of servers connected to that switch. Every switch will do it in a single step. It will do the operation and then send the result to the next level of switch. Okay, so now you see we reduced a n-step operation to a two-step operation. Two-step for a network size and a topology which is 2 levels of factory. Okay, this is one of the advancements in networking, where we start integrating compute elements so that high performance codes can be accelerated by offloading certain things into the network itself. Okay, and because you're able to do it in 2 steps, the top level switch is able to now share the aggregated result in a single go, but all the lower level switches can collect the data in less number of steps. And therefore, and by the way, if you look at practical application, I'm giving you a simple profile of a weather application called WRF. Okay? WRF is a weather application which is used for weather prediction and forecasting. It takes huge amounts of input data. It distributes it to multiple servers. All the servers now they need to talk to each other. And these are the various calls that they're doing. They are, MPI wait refers to the servers waiting for everybody to finish. Like they have to synchronize, right? When everybody is doing their job, one rogue person cannot keep doing whatever it wants. There has to be some synchronization step where everybody will come to their state, take the new data, and then start the next iteration. Then when everybody's completed the next iteration, it will again wait and then start the next one. So there are calls made in the system called MPI wait. You need to do reduction, which I talked about. You need to do some broadcast. You need to do some point to point. You need to do all reduce. So you need to do lots of communication operation. I just want to show you one particular operation which is there in this dark green and which is there in this brown. Okay, it is all reduce. Okay? You see that in a particular runtime, almost 20% of the time was spent in doing a reduction. And also for wait is one of the main thing, because most of the jobs are wanting to be run synchronous. Compute and communication has to synchronize, but you see there are collectives as well. So there was so much of broadcast, the blue part, there was so much of all reduction, and the reduction was only 4 byte and 8 byte. If you see this green line over here, and okay, so if we are able to do this particular portion inside the network, we will actually reduce this 20% to less than 2%. And therefore, network has actually helped in accelerating the compute. So it's an intelligent network. Okay, it is not doing only packet passing. This is one of the things. So just to give you some examples, MPI all reduce performance for a particular message size. If you look at small message size, you look at it as software versus hardware. When I say the dark green line, which is standard InfiniBand, versus the light green, which is InfiniBand with Sharp. If for a certain message size, I took 400 microsecond to complete an operation, with in-network computing enabled or with intelligent networks, I'm able to do it in around 60 microseconds. Generally, we are able to reduce 10 times the time spent on doing these kind of communication with intelligent networks. And this whole thing also is required for AI performance. Why? Because think about a simple image recognition, right? Whenever you do any training, forget image recognition, let's talk about simple training applications, right? Whenever you do any training application, what does it do? I mean, what does the neural network do? It actually takes in data. There is a parameter server which actually looks at, in every iterative step, it looks at all the data, input data, and tries to train itself by getting a new weight. Okay, tries to assign a weight, and this weight, the new weight, is a calculation done by collecting data from everybody, the delta from everybody, and then calculating a new weight factor and then distributing the new weight factor. Then again the next training cycle starts, where every training agent will again give its own delta weight to a parameter server, and then the parameter server will do some operation and again try to fine tune. So this is again the same kind of operation that I talked about earlier, right? And therefore it can also be mapped into network acceleration, which is what is done by the current intelligent networks today as well. So one thing is, so that is one technology, let's say. Okay, how do we apply it? So to apply it, let me go into a little bit of details of a computer architecture. a current GPU accelerated computer architecture. You all are aware of standard GPUs. You must have seen, I'm showing a current generation today's NVIDIA A100 GPU. It has certain amount of teraflops for floating point 64 performance. It has got certain amount of connectivity. You can see here different interconnects so that multi GPU can communicate to each other and solve a job. And therefore, and this GPU is then put into a motherboard. Multiple of them are put into a motherboard to form a GPU accelerated system. All these GPUs are connected to each other using very high speed interconnect, and they exchange data between each other. Okay. When you want to go out of a server, what if you need more than 8 GPUs for your training workload? There are clusters right now, if you look at top 500, which have got thousands of GPUs doing a single job. Okay? So you need to go out of that 8 GPU. So here we have connected those 8 GPU in a single motherboard. But if I want to go out, then I need to have those network cards. This is what I show in this picture. There are multiple network cards over here, right? They also connect onto the motherboard. And it forms a full GPU accelerated system. This is one particular building block of a particular supercomputer, right? So many GPUs on it, so many network cards on it. And this is how it looks like. If you look at the logical connection of various elements, it contains the processor, it contains some PCI Express switches. You would have seen any standard PC, there is a PCI card, right? How do peripherals connect into a server? There are PCI cards. PCI cards are put into slots which have their electrical signals coming from a PCI switch. Okay, so I'm giving an example of a particular GPU.
Ashwath, maybe I would just like to interrupt you. If you could only share the presentation, because this is all getting recorded. So if it's okay, you can because we can see all the pop-ups coming from the.
Oh, so sorry. How did that happen? Just hold on. Oh, you should have told me this earlier. Let me see, because there are a lot of pop-ups sharing. I mean, I was closing those pop-ups because it was disturbing me. I didn't know it was getting broadcasted as well. Let me stop showing screen and show my presentation. Do you see my slide now?
We are good to go.
Okay, thanks, Bharat. So now we're looking at a standard GPU accelerated server, okay, which has all these GPUs. It has got all these adapter cards, fine. But I want to create a cluster which is bigger than this. Okay, then I will connect multiple of these systems onto a single cluster. And again, I give you an example of that standard factory topology. Okay, what I do here is, as you can see, then I should be able to show my pointer as well. Yes. So what I do here is I take a GPU node with multiple GPUs inside, which has got multiple network cards to exchange data outside, and I connect it to multiple switches. Okay? And all these switches are in turn connected to another layer of switches, so that every node can talk to every other node without any blocking. Okay? When I have connected all these nodes in this particular manner, I form communication rings between the various GPUs inside the servers. When I form these communication rings, I am able to do those reduction operations that I talked about within the domain of these rings. So my switches can actually contribute to doing calculations of an AI workload as well. Okay? And that's the reason. And the reason I have connected my servers in this particular manner is to make use of the technology that I talked about earlier. So when you look at, so the whole point of this talk was design principles for high performance compute, right? High performance clusters. This is one of the design principles. You don't, when you create a large supercomputing cluster or a large AI or a machine learning cluster, you don't randomly go and connect anything anywhere. Why? Because you need to exploit all the benefits of the technologies that are present in high performance networks. And for doing that, you need to look at the internal architecture and connect it in a certain way. And when I say you need to do it, I'm not saying that every user needs to look into it, but every user should be aware of it. Finally, when it comes and gets deployed from a particular company or a particular institute, most of these things are taken care of. But when the user understands in depth of why it is connected like this, what maps to what, then when you do your parallel programming, you will try to pin things properly. You will try to pin the buffer of GPU1 to the adapter 1, or the data transfer that has to happen from the buffer of GPU1 should go from the adapter number 1. Okay. Again, it is all taken care of by the internal libraries that are built in, but those libraries are configurable, right? There can be systems which is like what I showed you right now, but there can be systems which might have a different kind of architecture. So to be able to tune the libraries, okay, so that the distribution of data and so that the distribution of buffers is done in such a manner that it can actually make use of the entire system with all the advanced technologies is the holy grail over here, right? So this is one thing. Again, what all does it give you? So I'm just showing you again the reduction bandwidth. If you were using nickel library, let's say you're doing CUDA, you have collective communication library from NVIDIA, it is nickel. If nickel was running as software, you would get a certain amount of bandwidth. As soon as you were able to do offload of many of the processes onto the switching element, you would almost double the bandwidth. Okay, so and that's the reason. Okay, this what I'm showing is this is actually the topology of one of the largest clusters that NVIDIA has, or one of the top, and it is also the topology of many of the largest supercomputing clusters in the top 500 list. It is connected in this manner, what we talked about. You know, you have got these compute nodes at the bottom which do a crisscross connection into a group of leaf switches, which do a crisscross connection into a group of spine. The number of crisscross connections versus the group number of switches in a group is all defined by what would be the most optimal way of offloading the collective operation. And then because it is such a large cluster, you need a third level of switching as well. Again, this is an example of a fat tree topology, a 3-tier or a 3-level fat tree topology. So the reason these clusters are made like this is because of all the things that we talked about till now. Okay. Now comes a question. So let's talk about some more advancements. You know, a very obvious question that comes into picture after seeing that complicated, large, you know, crisscross kind of diagram is, what if one link fails? I'm running a parallel job and suddenly one link fails. What will happen to all my mapping and all the things that I did, right? I tried to do so much of optimization. I created a network in a particular manner. I made sure that my programming was done, or programming was utilizing the library in such a manner that everything kind of came together into one big, you know, data center as a compute unit, right? But what if one of the link fails? Everything breaks apart, right? So therefore, you need to have some more intelligence in the network so that it can be self-healing. If there is a link failure, it should not be catastrophic. It should not break down your entire job. It should not be that you have to run your job from scratch. So let's look at some properties of that fat tree network. Again, I'm showing you a same, you know, 3-tier network. Lowest level is all the compute elements. Then level 0 is nothing but first level of switching, then second level of switching, and third level of switching. When server A, which is 0010, wants to send data to server B, it will send data packet to the first level of switch. The switch will say, hey, okay, it is meant for such certain server B, and I know that to reach that server, I need to send it out from a certain port. It will send the data from that certain port. The next level of switch will do the same thing. It will switch. When the data reaches the top level, it will switch down. Now when the data comes down, okay, it will go to the first level switch again and it will reach the destination. What if one of the uplink breaks? Over here, let's say one of the uplink breaks. The switch contained a table to route the data through this particular link. Okay, so when the data arrived to that particular switch, it said, hey, I don't have that link available anymore. Networks are intelligent. They have been intelligent for quite some time, that they can actually make a decision, and if one link is broken and if there is a parallel link available, which is there, it will route the packet through that parallel link. Okay, and data will again reach the destination. There is a certain characteristic of this kind of tree topology, is that if you have a downlink failure, okay, so as long as it is an uplink failure, you had multiple parallel paths. But if you had a downlink failure, there is a dead end, because there is only now one way to reach down. You don't have, for packets going down, you don't have a parallel path, because this endpoint does not have two ports in which one will connect to switch 1 and other will connect to switch 2. Generally in enterprise systems, you have a dual port adapter, that's fine, right? But in HPC systems, you don't do that, because when you put a dual port adapter, you actually reduce, for a certain amount of switching element, you automatically reduce the size of the cluster by half. The main aim is to make a very large cluster, not reduce it for resiliency. So better to have redundancy in such a manner that if you have these kind of failures, then something intelligent should happen. And that's what happens in these high performance switches. Right? Once a switch sees that there is a link failure, it sends out between the switches a failure in routing notification to all the switches which are in the critical path of the delivery port of a particular switch. Because of this, when data packet goes from server A to the first switch, it automatically reroutes it to a different switch and a different path, uplink path altogether. Okay, what it does is, so you would say, hey, why do I need to do this? Why can't I have, if data was not delivered, let my server send out a NAC and let it send out, let there not be any acknowledgement, because finally all these are reliably connected servers, right? So the transport mechanism is reliable. If there was data delivery that did not happen, and especially when it was an RDMA packet, you have to have upper layer protocols which make sure that data has to be delivered correctly, otherwise there will be memory corruption, which is right, 100% right, which is what used to happen in all the other networks, right? The network doesn't do anything. It is the endpoints which actually talk about resiliency, and if packet is not delivered, it will say, hey, I did not get it, please send it back. So data needs to be sent all the way back. But because of these intelligent networks now, because if there was a failure in any of the links, because the networks themselves are intelligent, you don't actually have to go all the way up to the software layer to request for a new packet. What does it mean in terms of latency? Rather than doing software level retry, which could be of the order of tens of milliseconds, we are able to do this route change in tens of, or maybe hundreds of nanoseconds. Okay, so therefore in a large cluster, even link failures do not result in degraded performance, because networks themselves are intelligent enough to communicate amongst themselves and create multiple tables, so that if there are failures or link breakages, packet will still reach. And because these networks do have n number of paths, n multiple paths between any source and destination, because it's a non-blocking network, and I will come to that part as well. We will now talk about the blocking factors in a topology. So we talked about in-network computing as one advanced feature. We talked about resilient network as an advanced feature. Now let's look at some other, one more thing maybe. Okay, so showing you the same diagram, showing you the same kind of diagram, a 3-level fat tree, okay, which has got again in the bottommost, I will show, as you can see, in the bottommost, you have nodes connected. The orange circles over here are nothing but the level 1 switch. Blue circles are level 2, and then you have red circles which are level 3 switches. Okay. Now think what is oversubscription and bisection. So now in a large cluster, let's say I have a cluster of 1,000 nodes. Okay. Now if I have a cluster of 1,000 servers, there can be communication. Think about communication when one node wants to talk to any of the remaining nodes. So there are 999 nodes that one particular node can talk to, right? So there can be there can be 999 ways in which traffic can go from one particular server to a destination server. Similarly, if the second node wants to talk to all the others, there will be again n into n, 999 ways. So the total number of ways that people or servers can talk to each other is given by n into n minus 1. For a 1,000 node cluster, it is 1,000 into 999, which is a huge number. Do you think there are those many numbers? Do you think there are 1 million cables in this? No, there are not. Okay. So definitely everybody does not talk to everybody simultaneously, but you can have any random pair of nodes which will start talking to each other, right? Depending on how your problem is distributed. So a 1,000 node cluster, you can make two sets of 500 communicating pairs, and you can then trace the route every pair will take. It is very much probable that many segments may get loaded by communication from multiple pairs. So now, even though I have a 100 Gbps link, I'm taking an example, even if I have a 100 Gbps injection into the fabric and my fabric is fully non-blocking. By non-blocking, I mean my lowest level switch have got 20 ports connected down to the servers and 20 ports connected up to other switches. So ideally, 20 servers can get 20 uplinks, right? So it is not blocking. No communication is blocking. If I had 20 ports connected down and only 10 ports connected up, in any all-to-all scenario, I would have actually blocked my uplink 2 times. But in a non-blocking network, ideally everything should work and everything is, everybody should get that 100 Gbps of bandwidth. But it doesn't happen because communication pattern in a cluster can be random. And because communication pattern in a cluster can be random, there can be segments which will be loaded twice. Because they will be loaded twice, the pairs of communicator which are sharing that particular segment will get only 50 Gbps if my injection was 100. Basically, they will get half of the bandwidth. This is the nature of any statically routed network. And this is very important because now if you look at, okay, we've not gone into topologies, but there are various topologies, right? I showed examples, I named fat tree, we talked about various kind of torus, we talked about dragonfly, hypercube. There are various mathematical way in which you can connect multiple switches to create a topology and create a cluster, but all of them are not alike. In a statically routed network, if you start doing what I did in the previous slide, that is to create communicating pairs and then see how many of those communicating pairs are able to get full bandwidth versus half bandwidth because some of the links might be double loaded versus 1/3 the bandwidth because there can be some links which are triple loaded. Okay, so x-axis on my graph over here represents the path sharing, means communicating pair for which there is a particular segment in my network which is loaded 3 times or 4 times or 5 times. So x shows the path sharing, okay, and y shows the number of communicating pairs in my cluster. So this graph actually plots how a statically routed network will look like for a 2000 node cluster. And this was a simulation done, so we have taken, and it's actually reality as well because it was done on a real system. We had a 2000 node cluster where you do artificial blocking versus different kind of topologies, and you can see that what is an ideal network? Ideal network is a network where all communicating pair will be at 1. So a graph which is a delta function at 1 represents an ideal network. That means I had a 1000 node cluster, I divided into two subsets of 500, and everybody had all their paths only single shared, so everybody got the same bandwidth as what they were injecting into the fabric. So delta function at 1 is an ideal network. Obviously you don't get an ideal network, but the graphs which are approaching the delta function are the better networks. Okay? So these are some of the ways in which you determine a network characteristic. And then comes another advanced topic of adaptive routing. I had a factory, so the number of links going into the fabric and the number of links in the fabric, I mean, they are, if I will always have an ideal communication pattern where everybody should get their bandwidth because I physically created a non-blocking network, but it's because it was statically routed, some of them got paths shared. This is where the concept of adaptive routing comes into picture, where the switches themselves can see whether their uplink paths are getting blocked. How do they see it? They see it by looking at the data packets which are queued for their uplink path. If that queue starts increasing so that it is not able to sustain the full bandwidth, the switch knows that that particular path is trying to carry data worth more than a single injection server. Therefore, it can actually now look at the queues of various outputs and it can try to distribute the uplink packets into these outputs dynamically so that every communicating pair of servers in a fabric will get full bandwidth. And this is what is achieved by adaptive routing. So all the new advanced networks, they contain adaptive routing as an intelligence built into the switch data plane itself. It is not a Ethernet routing algorithm of OSPF or BGP, which is like, shortest path network or something, which or ECMP for load balancing. No, because Ethernet, it's the control plane that does all the routing. But in high performance network, if you had a control plane doing this, by the time that the control plane is notified that there is a congestion, and by the time that the control plane is able to make a decision, the packets will be dropped because you're looking at such high bandwidth networks, right? Therefore, you need to have these routing decision making done in the minimum time possible by looking at the data plane itself, which is what all high performance networks do. This example, this is a paper from the Oak Ridge Coral Summit supercomputer, which is a very large computer, and where various adaptive routing algorithms were tried. And this part shows the network efficiency when it was statically routed, that is without adaptive routing. You can see this histograms show nothing but the blocking factor, means these many nodes actually were able to achieve near 100% of the bandwidth. There were many nodes which were sharing path, so they had only 50%. Then some of them had 33%, and so on and so forth, right? And when adaptive routing algorithm and adaptive routing based hardware was enabled on that particular computer, the same computer was able to show near 100% throughput, 94% to be precise, for all the communicating pair. So this is again 96%, sorry to be precise, for all the communicating pairs. So this is again, one more advanced feature for high performance networks. Okay. So I think we talked about a lot of points. I really don't want to be overloading with many. There are many other things. What I want to summarize is that we need to accelerate all the levels of HPC and AI frameworks to get a supercomputer working at its optimum performance from clustering and networking point of view. You need to look at enhanced topologies. You need to look at, I didn't cover many of these, so I will not talk about it, but we did talk about the transport offloads. These are the basics, right? RDMA as a transport offload, GPU direct as a transport offload. These are basics. Then large networks, self-healing. Okay? Congestion in the network, enhanced adaptive routing. On the communication framework itself, in network computing, where the network elements are taking part into computation. They are not only being communication engines, but also compute engines. So all these enhancements are fundamentals of today's high performance networks. We look at some specific technologies, as I showed in the previous session. We talked about various high performance networking technologies, but we propagate InfiniBand as a technology because right now it is one of the only existing technology for high performance networks. As I showed in that graph, there is not many proprietary networks. People are not making proprietary networks anymore because this is a standards based network. Just like Ethernet is a IEEE standard, RFP defined, similarly InfiniBand is IBTA defined, a technology standard, and there are tons of companies which are part of this consortium. NVIDIA leads it because right now NVIDIA creates all the elements of this network. It is standards based, so it is backwards and forwards compatible. It is architected to scale. We talked about scaling and the various technologies that are put into it so that it can actually scale up to thousands of nodes. It is fully software defined and centralized managed, as in there is no every switch in that network does not have any control plane processor. Like unlike a Ethernet switch where you can log into a switch and you go and say, hey, please run this protocol on it, please do a link aggregation, please do a OSPF, please do a BGP pairing. None of those switches do that. It is all managed by a central entity called subnet manager, which discovers the entire fabric, which puts the routing table into each element and so on. So it is like the epitome of software defined networking. And then finally, advancements like doing in network computing for both CPUs and GPUs are part of this. Okay? So I think with that, I will conclude my session. I hope it was informative and you would be interested in looking more into details for folks who are interested in the networking domain, right down from right up from fundamentals of electrical engineering with the phi layer to fundamentals of networking with the link and network and transport to the maths of graph theory and topologies to doing compute inside the network and looking at advanced algorithm for making networks more efficient. So again, thank you for joining. I think I think I finished the second part a bit early, so we have 10 minutes maybe for live Q&A if we need to. Let me open my. Okay, there is a question. Why can't we connect level 0 and level 1 switches laterally? Okay, good question. When you say laterally, you mean side by side, right? So yes, you can do that. It doesn't hurt you, right? But okay, since we have time, I will go to one of my previous slides, which I had actually skipped. So there are various ways of connecting. When you connect it laterally, you will form some random mesh. Okay, one thing we talked about is that you need to have a topology which is well defined in a certain manner, right? So let's say I have got this, this is my particular, this is my particular topology, okay? And when I created a two switch network, I connected it laterally between two switches, and therefore I got a certain size system. If I wanted to connect more switches, one way of making it is you can bring in a third switch and create a link. Okay. If I wanted more, I could make one more link, one more switch, bring in one more switch and make another link. But this will now not work. Why? Because it results. So all these high performance networks are credits based. That means servers connected to a particular switch can actually talk to servers connected to another switch only when the switch provides credit that yes, my path is free, you can inject a packet and it will be reliably delivered. So in a four switch scenario, when let's say a certain, and obviously you have servers connected to every switch here in this kind of scenario, right? So in this kind of scenario, when you have a server A wanting to talk to C, wanting to talk to D, okay, and E wanting to talk to B, and at the same time, all of these are wanting to talk to each other, you will result in something called a credit loop or a deadlock, because this is any network dislikes loop. If you look at Ethernet, you have STP, spanning tree protocol, right? If there is a loop in the network, it will actually break one of the links. If you don't do spanning tree, then you go to some layer 3 protocols where you have to do routing. InfiniBand or high performance networks are usually flat networks because you don't want to go into the complications of doing L2, L3 and all that. Everything is a flat L2 network. And therefore, if you connect switches in random fashion, you might end up with a loop. And this deadlock is catastrophic. When you hit this deadlock, the only way to break it is to reset everything. Okay? If you connect switches laterally, or there is, okay, I don't have that graph here, but yeah, if you connect switches laterally, let's say I connected two of these L1 switches between each other, I will actually create a four switch loop and I will end up into a deadlock. So InfiniBand or any high performance network, it has a certain routing algorithm which is suited for a certain way in which you have connected the switches. If you connect the switch in a fat tree manner, the routing algorithm knows that all the links are level to level and the routes are only up up down down. If you want to connect, now I did show you different topologies. I showed you hypercube and you can see that there are loops here, right? But hypercube does not run an algorithm. Routing algorithm for hypercube is different. It makes sure that it fills up the routing table of each switches so that there are no loops. Okay? Similarly, routing algorithm for Taurus is different. It's called 3D-TOR. Routing algorithm for a Dragonfly is different. So yeah, you can connect switches laterally as well. You just don't do it in a fat tree network. If you're doing it laterally, then you create a torus or a hypercube and make sure that the algorithm that you use while starting off a cluster is the algorithm which is suited to route that particular topology without creating loops. Okay, so that's okay. That now there is one more question. Does self-healing require sending packets in disjoint path? This creates redundancy but increases network traffic. Can we reduce network traffic with some network coding? So yes, self-healing requires packets to be sent, okay, between in disjoint paths, which is actually creating some amount of traffic. But this failure routing notification packets are a few bytes long. And anyways, high performance network contain because they don't have any control plane, they contain a virtual tunnel on all their physical links called a particular virtual lane, which is used to carry traffic only for the management between all the switches. So self-healing networks, when they are sending those failure FRN packets, the failure routing notification packets, they are sent on a dedicated virtual lane on which there is no data packet allowed. Okay, so InfiniBand, for example, as a protocol has 15 virtual lanes, and VL15 is reserved for all the management datagrams between all the switching elements in this topology to exchange running data, and FRNs are set onto that. So you actually don't end up eating away the bandwidth of your actual data path. Can we reduce network traffic with some coding? Okay, so number one, we actually don't affect network bandwidth here because we are anyways using that virtual lanes for transferring many of the management packets. And there are codings available at multiple levels. You know, when we talked about the PHY layers, there are coding at the PHY layer. For example, when I'm sending 100 Mbps, Gbps signal, my PHY itself is coded with 64 by 66 kind of encoding. So for every 64 bits sent, I will actually send 66 bits so that I can have 1-bit error detection and correction and all. And then there is forward error correction on top of it as well, Reed-Solomon FEC, which again does a block coding, right? 512 by 528 kind of coding. So those codings are there in various levels of network. They're already there. And that is actually, so that kind of reliability has to be built around in all layers of the network. There is one more question from Venu Kumar. How do I finalize the topology to be used? Does application matter? Absolutely, very good question. So if so, can you state some example of application for explanation? Okay, so 90% of the world's supercomputers are actually built with a factory topology. Why? Number one, it is very structured, and number two, because it is a non-blocking all-to-all kind of architecture, no matter what the application, you will actually find paths between the switch which will be non-overlapping. So if you have adaptive routing enabled, you can actually have any kind of application which can run on this network without much tuning required. Okay, that's the reason why factory is one of the most popular topologies. Hypercube and toruses are also popular, but they are popular for very specific computers which run applications which have nearest neighbor communication. Okay, for example, if you see a torus, every point is actually has got very fat connectivity to its nearest neighbor. But if it wants to send data to one corner node, it will actually have to traverse lot of switching elements in between. This is what is called the diameter of a graph. A ND torus, or let's say a 6D torus or a 3D torus with 10 by 10 by 10 switching elements will have a worst case hop count of 10. A fat tree with 1000 nodes will have a maximum hop count of only 3. So the graph diameter of a fat tree is much less. Okay? And therefore, you can actually, there are other topologies like Dragonfly Plus, which has got even lower graph diameter. But basically, fat tree is able to take in varied kind of applications with varied communication pattern, whereas things like toruses and hypercubes are good only for nearest neighbor communication. The applications which are nearest neighbor communication are mostly MD kind of simulations. Okay, if you're looking at, for example, a CFD simulation where you many times solve things in the Fourier domain, you actually will end up doing a matrix transpose, which will result in all-to-all communication. You will run a routine called ptrans, which will result in all-to-all communication. And when you do all-to-all communication, torus is not a good topology. So if you see any large torus machine, they are doing CFD workloads only for a small subset confined to the servers which are connected in the nearest neighbor switches. Whereas with fat tree, you can do whatever. So yes, there are various things that you need to see. I gave an example of WRF. Now, if you really want to make an application specific only computer, WRF, if you profile it, it only contains point-to-point communication between node plus 1 and node plus 4. So if you connected a system with every node connecting to its nearest neighbor and its fourth nearest neighbor, WRF will run perfectly fine, and you don't have to have so many switches in between. But then that network will only run WRF, nothing else. Right? So that's like some views on topologies and applications and mapping. There is another question. Is it possible to virtualize capabilities like RDMA? Oh yes. So RDMA works over single root IO virtualization, SRIOV. Okay? You cannot virtualize it with standard para-virtualized device, right? You need to have SRIOV, wherein you have to do one particular adapter card when enabling SRIOV shows itself as multiple virtual functions, which can be directly passed through to the VM. And the VM now needs to run the driver for the card, but every VM will have its own resources available. Obviously, when all the VMs are communicating outside of the network, then the total bandwidth will be equal to the aggregated bandwidth, obviously, because that's the physical port that is connected. But virtualization is done in InfiniBand as well. Usually, you don't do virtualization in InfiniBand because the whole point of making a large cluster is that you have one job that spans across multiple nodes. People did virtualization because they had large node and they had multiple jobs. So you wanted to divide the resources, right? And in HPC and parallel training workload, it's the other way around. You want to make one large system to run one particular workload. So you don't need to virtualize. However, that said, a very interesting thing happening in today's world is cloud native supercomputing, wherein you have created a large supercomputer, but every time it is not being used for running one single large job. There are tons of users which are working on it, okay, and they might be needing multiple nodes, but they might not be needing the whole system. So you do need to have, if you want to have best utilization of your resource, yes, you virtualize and then you combine multiple servers for tenants requesting a parallel job, and you give parts of servers for tenant, or you do bare metal, single bare metal to tenant requesting a serial job. And in cloud native supercomputing, you virtualize using SRIOV and you can manage using standard OpenStack. Again, this is one of the active projects. If you just Google cloud native supercomputing, and you'll see lots of collateral on the web. Okay, I think we'll take one last question. Can you please add some comment over deadlock? So maybe I'll send out. We'll be responding to many of these questions over mail as well. So what I'll do is I will send out a link to a nice write-up which explains very nicely how that deadlock happens, even doing some amount of animation, and which explains the credit-based routing fundamentals of technologies like InfiniBand. So I think there are no more questions, and we are dot on time. It's 7. So let's stop here, and over to you, Bharat. Anything, or we can just close?
Close. Yeah.
Okay. Thank you. Thank you all for joining. Bye.